Investigate the buried materials or interfaces using X-ray techniques, we have basically two options. First one is to use bulk sensitive techniques such as photon in, photon out, X-ray, which is example is X-ray absorption in fluorescent yield. Or the other option is to use surface sensitive techniques such as photon in, electron out, or XPS that we just introduced. Both these approaches have their problems. So in the first case, the information we obtain is averaged out in depth, and it's very hard to discriminate interface from the bulk information. In the second case, signal attenuation causes that it's even challenging to reach the interface or the buried layer. And even if we are actually successful, some interesting parts of the information, such as bottom of material A here, are lost because the most of the information comes from above, from the top and from the bulk of the material A. The solution that we are actually providing is to use standing wave enhanced photoemission spectroscopy with higher excitation energies by actually modulating electric field, or we can think of it as an intensity of X-rays inside the sample. We can enhance the signal from the interface or from any other depth that we can engineer our sample to specifically do that. Then this technique can clearly actually distinguish interfacial and the surface and bulk phenomena. Let's now look at the mechanism how we create the standing wave. We use multi-layer mirrors, which are not too different from the ones used in EUVL optics, and we are using Bragg actual reflection geometry, which in short means that we use monochromated X-rays and tune the incident angle to fulfill the Bragg's law here. By doing that, we actually drastically enhance the X-ray reflectivity, and strong standing wave with vertically positioned nodes and antinodes is created. By slightly changing the incident angle, we are then able to sweep the position of these nodes and antinodes actually vertically by half of the standing wave period, and practically illuminate different depth of the sample. It is also important to say that the period of the standing wave equals to the period of the multi-layer mirror, and this gives us a very nice handle how we can engineer the sample and engineer the shape form of the standing wave to match the needs of the material we want to study. If we now look at the dependence of the signal intensity as a function of incident angle and depth, we can see that for a specific depth, one obtains a very unique intensity profile, also known as a rocking curve, as shown on the blue curves on the right. The shape of these curves, which are the quantities that we will measure in our experiments, is changing dramatically with the depth. And this feature really adds the depth sensitivity to our experiment. Also, what you can clearly see on the color panel on the right is that as we go deeper and deeper, the intensity of the signal gets attenuated more and more. The first example I'm going to talk about is self-assembled monolayer photoresist that we studied earlier this year. The uniqueness of this sample is its relatively small thickness, which allowed us to use a multi-layer mirror with a period of only 34 angstroms. We used silicon moly mirror as our standing wave generator, and then the additional buffer of aluminum oxide was grown on top. The SEM photoresist was then deposited on top of alumina. The schematics on the left shows the mechanism and the data collection of our experiment. Monochromatized light was shined onto the sample in Bragg geometry, and as we slightly changed the incident angle, the standing wave was swept up and down through our layer of interest. We then collected photoemission signal from different core levels as a function of incident angle, and this is shown in the panel in the middle for carbon, aluminum, silicon, and moly. The evolution of these experimental intensities, the experimental ones are shown in the open circles, was then actually modeled by using X-ray optical simulation package, and the simulated curves are shown as solid lines. The solution of the optimized structure that shows great agreement between experiment and theory is shown on the right here. First finding is that the alumina layer is actually surprisingly flat, and the interface between polymer and alumina is very sharp with just a few angstrom of interdiffusion. Photoresist itself has a mean height of around 18 angstroms, which is also interesting because the length of the molecules that we used is over 23 angstroms, and therefore we can see that these molecules are not standing upright nicely perpendicular to the surface, but they're most likely tilted. Other surprising finding was that the top of the SAM film is relatively rough and exceeds even past 23 angstroms. We concluded that the self-limiting process after the first layer growth wasn't actually working perfectly, and in some places the second layer of polymer started to grow. These results were encouraging, and we wanted to move to study somewhat actually thicker films, and I'm going to show those next. In the next example, we used chemically amplified photoresist, uh, which was spin coated with nominal thickness of 10 nanometers. Because of the actually thicker overlayer, we also used the mirror with larger period, which was also 10 nanometers in this case. Schematics of the sample are shown on the right. So by looking at the initial X-ray photoemission spectra, as shown on the left, we see all elements that we expected. So top four spectra are originating from the resist, and they are carbon 1s, sulfur 1s, fluorine 1s, and oxygen 1s. Bottom two from silicon and moly are again two materials from the mirror. One interesting thing to notice is that the carbon 1s was actually deconvoluted into two spectral components, high binding energy and low binding energy 1. Low binding energy corresponds to carbon-carbon bonds, and that's something expected to dominate the spectrum because this is the backbone of the polymers that are used. High binding energy corresponds to states where part of charge from carbon is transferred. So this can be, for example, a case of carbon-oxygen bond groups. So as we showed on the next slide, the distribution of these two carbon